For my Unit 2 portfolio, I chose my Athletes or Mathletes project to showcase the Unit 2 standards. While I'm on the court playing volleyball, I constantly am thinking about the physics behind the sport. I chose to analyze the physics behind my jump serve. The first part of the project was to pick a video and fill out a data table of known values that included the following: acceleration in the y direction, acceleration in the x direction, ending y displacement, ending x displacement, time of flight, maximum height, launch velocity, and launch angle. From the video, I was limited to estimating times and distances. To estimate time, I used the seconds on the video and estimated to 1/10 of a second. I estimated distances by comparing events in the video to a diagram with accurate measurements of the court. I estimated distance to a half meter. For acceleration in the y direction, acceleration on the y-axis is constant. It is always negative 9.8 meters per second squared due to gravity. For acceleration in the x direction, ignoring air resistance, acceleration in the x direction is always 0. For the ending x displacement, my serve started at the end line and ended between the opposite 3-meter line and the end line for a total displacement of 16 meters. For the ending y displacement, my serve starts about 2.5 meters above the floor. I made this estimate based off my height and how high I jump. The end point was estimated at 0.5 meters based on my opponent's posture. Therefore, the y displacement is 2 meters. To estimate the time of flight, I used the seconds on the video from when I contact the ball to when the opponent touched the ball. I got 1.2 seconds. I estimated the maximum height at 3 meters based off the height of the antenna, which is also 3 meters. I could not measure the launch velocity or launch angle from this video. To fill out the calculations data table, I had to choose 5 points along the trajectory of my serve. I labeled these 0 through 4. Point 0 is the start, point 1 is the maximum height, point 2 is when the ball returns to serve height, point 3 is 1 second time of flight, and point 4 is the end point. This allowed me to calculate the unknown values in my data table using kinematics equations. Looking at the first column of the data table, I know T0 is 0, T3 is 1 second, and T4 is 1.2 seconds. In the next column, I know X0 is 0 meters and X4 is 16 meters. In the Y column, I know Y0 is 2.5 meters, Y1 is 3 meters, Y2 is 2.5 meters, and Y4 is 0.5 meters. We don't know the velocity in X. In the next column, we know that Vy1 is 0 at the apex. The next two columns, AX and AY, are constants of 0 and negative 9.8 meters per second squared. We don't yet know the absolute velocity, but we do know that theta 1 is 0 since Vy is 0. In other words, the ball is traveling horizontally. Now we must solve for the missing values. I started by solving for the velocity on the x-axis by dividing the distance traveled, 16 meters, by the time of flight, 1.2 seconds. The result, 13.33 meters per second, stays the same since AX is 0. In other words, the x velocity is constant, so we will fill the Vx column with 13.33 meters per second. Next, I calculated the time of flight to the apex, T1. This also allowed me to calculate Vy0. Since my point 2 is when the ball returns to the initial height, Y0, I know Vy2 is the opposite of Vy0 at negative 3.13 meters per second, and the T2 is twice T1. With T1 and T2, I calculated the x displacement by multiplying T1 by Vx1 and T2 by Vx2. I continued down the table calculating x3 in the same manner since T3 was 1 second by my choice. I calculated Vy3 by using the previous Vy2 as my V0 value in the equation V equals V0 plus 1/2 AT squared, and T is T3 minus T2. I used the same strategy to calculate the Y3 displacement. I continued the strategy to find Vy4. Now with all my velocities, I calculated values for absolute velocity and flight angles using Pythagorean theorem. Finally, I checked my values against the video to make sure they make sense. I plotted my vector diagram to mimic my video. On my diagram, the ball flies from right to left. At each of the data points, blue vectors represent Vx and Vy. The resultant vector, green, is absolute velocity. A red vector pointing straight down represents Ay. Next, I graphed a distance versus time graph and a velocity versus time graph to showcase my data. For the distance versus time graph, I plotted the x displacement, y-axis, versus time, x-axis, in blue. I also graphed the y displacement, y-axis, versus time, x-axis, in red. For the velocity versus time graph, I plotted the Vx velocity, y-axis, versus time, x-axis, in green. I also graphed the Vy velocity, y-axis, versus time, x-axis, in blue. From this project, I can conclude I learned the value of creating a diagram of the trajectory with numbered labels for each critical point. The numbered data points made it easier to choose the right data in equations that use v and v0, for example. Calculating absolute velocity and theta helped me understand why jump serves are so much more effective than standing serves. The added height of the jump adds velocity and angle to the receiver's challenge. Let's end my portfolio by watching my beautiful ace one more time.